Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is how to perform battery impedance testing with the Megger BITE instrument. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Jason Aaron, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Volny Naranjo, Senior Applications Engineer, and Sanket Olar, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Jason.
Okay, thank you, Michael, and welcome everyone. Thank you for joining us today. My name is Jason Aaron. I'm a substation applications engineer with Megger, and today we will discuss how to perform battery impedance testing with the Megger BITE instruments. Our agenda for today will include a brief introduction to battery testing in theory, some different types of test measurements, some pre-test considerations, and how to use the BITE test instruments, followed by a look at the PowerDB, test form for battery testing. Let's get started. Substation batteries are a key component to any power distribution system. They provide a source of backup power when our main source fails, and in many cases, the power for operating protection and control devices. For these reasons, it's critical that we know that we can rely on these systems and that our batteries are able to support the load whenever we do have an outage situation. However, batteries do have a limited service life, and they're designed to operate for many years, but they must be maintained to properly do so. This is why it's important that we track the health of our batteries so that we can predict battery failures and plan maintenance actions to extend the lives of our batteries. So to be able to do this, we have 2 options per IEEE standards. We have the capacity test, which is the main option, and a capacity test or a load test is an easy to analyze test. And whenever we're done doing this test, we are going to know the true capacity of our batteries. However, there is some drawback. The capacity test requires a large amount of resources and planning, and it also requires a battery backup depending on how your system's designed, or in some cases, this isn't even an option and the test has to be performed with your batteries offline. Additionally, if this test is done wrong, you can harm your batteries. So typically you want to limit the amount of times that you do a capacity test over the life of the battery. This is why the test is usually performed every 3 to 5 years. However, we do have a second option to help fill that gap between capacity tests, and that's battery ohmic testing. Now, we can see in our graph over here that there is a correlation between the ohmic values that we would get and the capacity of a battery, and that's why we can use this method to help us evaluate the health of our batteries between those tests. Now, the ohmic testing alternative that we have is it's a test that we can do online, and it's low cost in comparison to capacity testing. The test is easy to perform, and it does provide a lot of valuable data without having that big logistical investment. However, this test does require some preparation to ensure that we achieve quality results. And once we get those results, it does require some interpretation, as ohmic testing doesn't have a hard, fast value that we're looking for whenever we take those measurements. To help us do this, it's important that we utilize consistent testing practices to get good results. And we also have to carefully follow good testing procedures so that we can produce quality trending data so that it is useful to evaluate the health of our batteries. So keeping all this in mind, today our presentation is going to cover recommended practices, test procedures for measuring ohmic values, and then we're going to go over the use of the Megger BITE products. Now, ohmic testing techniques, whenever we talk about that, we have to consider a couple things. So batteries have resistive, capacitive, and inductive characteristics. And that ohmic equivalent, we can measure that. Now, we can do it a couple of different ways. We can either do it with an AC signal or a DC signal, and that equivalent value is either going to be an AC impedance value or a DC resistance value. Now, as the battery ages or deteriorates, these ohmic values will change, and this value is going to be a direct reflection of the condition of the battery. This is why we can use ohmic values to determine if a battery is deteriorating. This, in turn, is going to allow us the opportunity to either change the battery or determine what type of maintenance may be necessary. So, what type of ohmic test should we use? Well, batteries have capacitive properties, and that can become non-uniform over the life of the battery as the battery ages. And these capacitive properties often will change before the resistive values of the battery. So by applying the impedance method, it's going to allow us the ability to identify problems more quickly than if we were to utilize the DC resistive method. Now, when we do use the AC method, frequency comes into play. So what frequency should we use whenever we do that test? Well, a low frequency signal is preferred as the capacitive properties will become more predominant at low frequencies. And we can see here by our formula for capacitive reactance that the capacitive reactance is inversely proportional to the frequency. So the lower the frequency, the higher effect of the capacitance. This is why we prefer to use a low frequency impedance method for ohmic testing. So let's talk a little bit now about how we do that test and how the impedance test works. So the concept of the test is we're going to inject an AC current into the battery bank, either through the entire string or cell by cell, depending on which BITE instrument you have. In this case, we're pushing current across the entire string, and the signal is that we generate is low enough that we aren't going to affect the battery or the load that it's supporting. However, the signal is high enough to help us avoid any ripple current interference or any noise that might be on the system. Now, once the current is circulating through the string, we can measure the voltage drop across the cell. And then by applying Ohm's law, we can calculate that impedance value. Using this method, you obtain both the cell impedance value and you can record the cell voltage. Now, some of the benefits that we have by using this method is there's some additional information to help us evaluate our batteries. Now, one of those is being the flow current of each cell, since we've already measured that value, and it gives us a good idea of the state of charge of our batteries. It also gives us an opportunity to measure for ripple current, and in some cases, we can also measure the float current. Now, this creates an added value to the ability for evaluating the health of our batteries and provides more information than just the individual impedance value of the cell. Another thing that we can look at is that it helps us verify the string continuity. And we can do this because we inject current throughout the entire battery string. Now, verifying the string continuity is a NERC requirement, and NERC mandates that you must verify this to ensure the battery string will deliver the expected voltage and support the system load when needed. Now, one method is to turn off the charger and see if the battery string can support the load. However, it's safer to circulate a current through the string and verify that there are no significant current losses. And therefore, this helps us verify the continuity of the string more easily. So now let's take a look at this table from the IEEE 450. Now, in this table, we can see that there is a correlation between impedance values and the capacity of a battery. Now, we also see that the majority of failure modes will work to increase impedance of the battery here. And that also, as the impedance increases, the capacity of the battery decreases. However, in some cases, the effects of these failure modes can be nullified or reversed if proper battery maintenance is performed. So now that we've discussed battery testing options and some of the theory behind that, let's move on and discuss some different types of test measurements. So the first measurement that we're going to talk about is ripple current. Ripple current is a product of an AC voltage that exists on a DC circuit. Now, this has a direct correlation with the health or efficiency of your battery charger. The charger is supplied with an AC voltage, and then it rectifies that to a DC signal for charging your battery string. And battery manufacturers have stated that less than 5 amps of ripple for every 100 amp hours of battery capacity is acceptable. But ripple current higher than this is going to create an internal heating effect on the battery, and this internal heating will age or deteriorate your batteries faster than expected. Also, ripple current can increase as the electronic components in the charger age. And this is why it's important to measure ripple current periodically and avoid that negative effect that it can create on your battery life. Because of this, the ability to measure ripple current has been designed into Megger's battery impedance test sets. And so now let's talk about float current. Now, float current is the amount of current necessary to maintain the battery string at the appropriate voltage level. And the float current value can help you identify whether the batteries are in a state of charge or discharge. And when the batteries are properly maintained and in a fully charged state, the float current value should be relatively small. On the other hand, discharged batteries will have a higher float current until they return to a fully charged state. Now, in some cases, you may have a higher float current value when the battery string is fully charged. This could be an indication that you may have an internal battery problem, such as a hard or soft short. Now, what you can do for this is this is a sign that we do need to take some impedance measurements to help evaluate our battery string. And this will allow us the opportunity to narrow down why our system is experiencing higher float current conditions. So strap resistance, float voltage measurements are an indicator of the state of charge of the cells in the battery string. The cell is in a state of float whenever it's fully charged and only needs the amount of current necessary to keep the cell fully charged. A normal cell voltage tells you that the cell is charged. However, more importantly, an abnormal cell voltage can also tell you something about the condition of the cell. A low cell voltage can indicate a shorted cell or an incorrect charger setting. However, another scenario for a cell with a low voltage involves the string overall. Now, remember that the battery charger is set to maintain a minimum voltage across the entire battery string. Well, if you have one cell that has a low voltage, the other cells are probably being overcharged to help meet the setting of the battery charger. And this in turn could cause other problems with the rest of the string. So for this reason, it's important to investigate any cell voltages that deviate from the string average or the rated float voltage. So our strap resistances and the inner cell straps are important to make sure that we test these. Now, whenever we're testing for these, we're looking for loose connections between the straps and the battery posts. The loose connections can create hot spots or elevated internal operating temperatures of the batteries. And this can be detrimental to your system. To take these measurements, you'll measure the strap resistance between two adjacent battery cells. Now, it's important to mention that whenever we take these measurements, that we have proper probe placement. You don't want to place your probes on the hardware connecting the strap to the post. You want to place your test probe connections on the posts of the battery so that you test or take a measurement across both sets of bolted connections. The strap resistances across the string, once you get these values, need to be compared and evaluated. Any big differences in values that you see should be investigated. And One of the things that you may need to do is disconnect that strap and clean the connections, and then reapply the strap and properly torque the connections, and then retest. One of the effects that open or loose connections can have on a battery string is it can cause a total failure. And what happens is normally your battery string doesn't have a large amount of current, flowing across it. However, in an emergency situation, you have a sudden increase in current, and this can cause major problems if you have loose connections across the string. Now, this is why it's critical that we measure strap resistances as part of our battery testing regimen. So temperatures can have a severe negative effect on a battery to shorten its life. So for every 10 degrees Celsius increase in temperature, the life of a battery is cut in half. Now, this increase in temperature causes acceleration of other battery failure modes to rapidly decrease the battery life. And when you're performing battery impedance tests, it's essential to record ambient temperatures. IEEE also recommends taking temperature measurements for at least 10% of the battery string. The cells you choose to do this for are going to be identified as pilot cells. And you need to label these cells so that you know which ones you took these measurements from. That way, you take your temperature measurements from the same cells every time that you do a maintenance interval. Now, the drastic effect that temperature can have on your batteries make it really critical that we ensure our batteries are operating at recommended temperatures. Test repeatability is really important whenever we do these tests. Now, the values that we get, like I said before, they're compared. Now, so being able to produce consistent results is really important. And the way that we do this is by having proper testing techniques and by having the same procedures that we apply to the battery every time. Now, a couple of things that are recommended whenever we talk about this are, one, the battery string must be in a fully charged state, and it also must be in a float condition every time that we take these measurements. We'll take a little bit deeper look into that later in our discussion about how to do that. Another recommended practice is in regard to using the same test equipment and measurement techniques every time that we do our battery testing. What this means is that whenever possible, you want to use the same test set, the same test probes. You want to apply your probes in the same manner, and again, make sure that your battery string is in the same prepared state every single time that you take these measurements. So now let's move on, and we'll discuss and talk about some of the pre-test considerations for our test. So evaluating the health of your batteries is highly dependent on the input data we provide. And the best way to do this is by following thorough testing practices. The ohmic values that we obtain are very dependent on the aspects of this, both before and after the test. And so this preparation needs to be done so that we can ensure that we do this. We also have to pay attention to the techniques that we're using whenever we're taking these measurements so that we can achieve good results. You also need to have an idea of what you're looking for whenever you take these measurements. That way, if you have any questionable test results, you have the opportunity to take a look at that and investigate it before you leave the site or move on with other maintenance activities. It'll give us an idea of the type of maintenance needs that we have for our battery string. So it's essential that we follow these practices so that we can provide quality data that we can rely on over the life of the batteries. Now, to prepare our batteries, one thing that we have to think about is for flooded cell batteries. If you do have flooded cell batteries, you have to check the electrolyte levels of those batteries at least 2 weeks prior to performing these tests. And if you do have any cells that are low, you want to go ahead and top them off at this point, because you don't want to do anything to disrupt the state of the batteries between this 2 weeks and when you're doing your testing. Another thing that you're going to want to do is 72 hours prior to testing, you're going to want to equalize the battery string. Now, it's critical that after you've done this equalization in that 72-hour window, that you don't add any electrolyte or try to re-equalize the batteries, that you allow them to float for that 72 hours before you do your impedance testing. This amount of time may vary depending on the kind of batteries you have, so it's important that you refer to manufacturer's information to make sure you're properly preparing your batteries for this test. So it's very important to closely follow these procedures so that we can produce quality test results. So before we move on into how to do our battery impedance test, let's talk a little bit about battery safety. So due to the hazards presented by a battery string, there are a few things that we should have available and some other requirements that we need to follow before we do these tests. Now, when you're in a battery room, you need to have an idea of where the fire extinguisher is located and that there's a neutralizing agent available for the batteries. Also, you need to have an idea of where the closest safety shower is in the event that you are exposed to any of the chemicals in the battery. Also, while you're handling the batteries, you need to make sure that you have all the appropriate battery PPE that you need, such as rubber gloves, an apron, and a face shield. And in addition to this, you need to follow any other PPE requirements that your company or the work site may have. You should also utilize any arc flash protection and also wear flame retardant clothing where it's appropriate or required. The last thing that I'd like to mention for battery safety is a work permit and your safety paperwork that may be involved with that. And you want to know whatever the job site requirements are for that. And this may be a job safety analysis, a job hazard analysis, or in some cases, an electrical work permit. You also need to make sure that you know what the exact requirements are for that site and that you understand the hazards involved whenever you are doing battery testing. So now we're going to move on to our next section where we're going to cover the test procedures for battery impedance testing. So for battery impedance testing, we have two options. We have the BITE 2P and the BITE 3. They both offer the ability to record ripple current, cell impedance, take voltage measurements, and measure the inner cell strap resistances across the string. However, there are some small differences. First, we're going to look at the BITE 2P and how to set it up and how to use it to take measurements. Now, the BITE 2P allows us to test with the system online, and it can be applied to battery systems with a capacity up to 7,000 amp hours. Now, as we said earlier, ripple current, it's important that we do cover that whenever we're doing these impedance tests, and the BITE 2P does have the ability to measure that. Another feature that the BITE 2P that sets it apart or makes it unique is that it has an onboard printer. And so after you record your measurements, you can configure the instrument to print your results and evaluate these before you ever leave the job site. This is really helpful to make sure that the data that you have is quality data. And if you need to go back and remeasure anything or do any kind of investigation before you leave the job site, you can do that. You can also configure the unit to download your test data using PowerDB if you choose to evaluate your batteries that way. Also, the last thing I would like to point out is that earlier we talked about verifying the continuity of the battery string as a NERC requirement. Well, the BITE 2P uses a set of current injection clamps connected to each end of the battery string to provide the current source for taking our impedance measurements. Because we do this, we inject the current across the entire string, and you can, while you're doing this, you can look for any significant current losses and therefore verify the continuity of the battery string. So now let's look at the hardware for the BITE 2P. So first we have the current transmitter, and the current transmitter is used to inject current across the string, charge the receiver before the test, and print our test results. When you're using the transmitter, it's imperative that we make sure that we have a good, reliable 120 volt, 60 hertz power source. Next, we have the receiver and potential probes. The receiver unit is used to configure the test, and it will store our test measurements whenever we're performing the test functions. And the probes work as a set to take the measurements across the string. We also have the current transformer, or CT, that's used in conjunction with the test probes for taking impedance measurements. This amp clamp CT is applied to one of the inner cell straps of the battery bank and measures the amount of current flowing across the string. This current measurement is then used to help us calculate the cell impedance values. And lastly, we have the red and black current injection clamps, and they're connected to the transmitter unit and then applied to the battery string to inject current that's being supplied by the transmitter. So something else that we need to talk about as far as setup is making sure that the instrument is charged before we take test measurements. Now, to do this, it's different for the BITE 2P and BITE 3 instruments. For the BITE 2P, the receiver probe is charged using the current transmitter. Now, the test kit comes with a charging cable, and the charging cable is connected to the receiver pistol at the rear of the probe, and then the other end of the cable is going to connect to the transmitter unit at the J4 connector. Now, after you've done this, to begin charging the receiver, you're going to press the green charging button that we see illuminated here. And then the red LED light is also going to come on. Now, the indication that the receiver is done charging is that red LED will start to blink. So to be able to set up our test with the current transmitter, this is an example of it here. And what you're going to do is you're going to have your red and black injection clamps are going to be connected to the current transmitter, and then you're going to have the red injection clamp applied to the positive post of the first battery in the string, as you can see here on cell number 1. And then the black injection clamp is going to be connected to the last negative post of the string, in this case on cell number 6. So after we've set that up, we can apply the CT around one of the inner cell battery straps of the string. So in this case, we're going to connect it around the strap between cells 3 and 4. Now, it's important to mention that whenever we're doing our impedance test, whenever it comes time to take the strap resistance on that strap, we need to move that CT to a different strap in the string while we're taking that measurement. So now let's talk about setting up the receiver, and this is what we're going to use whenever we're taking the measurements on the batteries and the strap resistances. So what we see here is that we have the receiver and the potential probe and the CT are going to plug into the bottom of the receiver unit. Now we can see that from the example here, and the CT is going to plug into this 4-pin connector at the bottom of the receiver unit. And then the potential probe is going to plug into the 7-pin connector right next to it. So now we've covered that, let's talk about how we're going to configure the instrument for the test. So to begin doing that, the first thing that we're going to do is we're going to press that green power on button to power up the instrument. Now, once it's on, we're going to use these up and down arrows to scroll through the prompts, and the up arrow is going to be for yes, and the down arrow is going to be used for no. Now, the first prompt that the instrument is going to ask you for involves the WAN barcode reader. Now, the WAN barcode reader is an optional accessory, and what it allows you to do is it allows you to associate your string information with a barcode. So if you do have that option, you're going to press up for yes, and then you're going to enter the string information for your battery bank, and then you're going to associate that with a barcode. If you don't have this instrument or you don't want to use that option, simply press down for no, and then you'll move on to the next prompt. The next prompt is going to ask you about baseline information. Now, this baseline reference, it'll help you evaluate your battery string against a value that you already know that you're looking for if you have that information. what it's going to do is you're going to enter that baseline test value, and then you're going to enter tolerances for a warning and alarm setting in the receiver unit. If you don't have that information available, go ahead and press the down arrow for no, and then proceed to the next prompt. So now it's going to ask you whether or not you have a split strap situation. So a split strap configuration on the batteries, what that means is when you have 2 or more battery straps for the same 2 posts on a battery. And you can see here in our the picture here that this is a, excuse me, having trouble with my laser pointer. Okay, that's not, okay, that's not working. So you can see in the picture that we have a split strap situation where you have 2 straps for, you know, the same post. So the way that this works is, let's say that you have 4 battery straps and you can only get the CT around 2 of those straps. So what you're going to do is you're going to take the total number of straps and you're going to divide it by the number of straps that you can get that CT around. So 4 divided by 2, your multiplier is going to be 2. So go ahead and enter that value into the receiver and push the enter button. However, if this isn't the situation that you have, go ahead and press down for no and then proceed with the setup. The next thing that it's going to ask you about is terminal impedance. So what terminal impedance is it gives you the ability to measure essentially the cable that comes from your battery charger to the first positive post of your string. Now this is going to be referred to as strap 0. If you want to measure this value, go ahead and hit up for yes, and it's going to allow you to take that measurement. If you don't want to do that, or your configuration is something as in a design where it just doesn't make sense to make that measurement, go ahead and press no, and you're going to move on to the beginning of the test. The next screen is going to ask you to verify the settings to be able to start your test. Go ahead and press up for yes to start the test. If you press down for no, it's going to take you to the very beginning of the configuration process of the receiver. So it's good to keep that in mind, that you pay attention to what's going on whenever you're setting up the instrument. So the very first measurement that the BITE 2P asked for is the ripple current measurement. Now, whenever we take this measurement, it's going to take the measurement using the CT that you've already applied to the battery string. So all you really need to do is refer to the screen on the receiver to see if there is any ripple current. And whenever you have a stable reading, go ahead and pull the trigger on the receiver unit to save that value. Now, the next prompt is going to ask you to connect and power the current transmitter. Now, we've already connected it to each end of the string. However, let's look at how to go ahead and inject current. So what you're going to do is you're going to push that green current on button, and it's going to illuminate green. Now, as the capacitors in the unit warm up, and we wait on that process, then the yellow current ready light is going to come on. And whenever we have a current that's being injected by the unit, we're going to see 11 amps on the ammeter on the transmitter. So the next step that we're going to do is we're going to go back to our receiver and refer to the screen, and we're going to look for a current value. And we can see here that we have 11.2 amps registering on the receiver unit, and the current transmitter says that we're outputting 11 amps. This is an acceptable reading, and we can go ahead, pull the trigger on the unit to record that value, and we can move on to taking our impedance measurements at this point. So to take the impedance measurements, what you're going to do is you're going to apply the probes across the battery in this manner. The red probe is going to be applied to the red positive post, and then the black potential probe is going to be applied here where the black arrow is. And once you have a stable reading on the screen of your receiver, you're going to go ahead and pull the trigger to save that value. So after you've recorded the impedance measurement and the cell voltage of that first cell in the battery string, you're going to move on to the following strap. So you're going to leave the black probe on the negative post of battery number 1, and you're going to move the positive, excuse me, the positive red lead or the receiver to the positive post of cell number 2, thereby measuring the strap resistance on the strap between those two cells. And again, whenever you have a stable reading, go ahead and pull the trigger to save that value and move on to the next cell. So now let's talk about finalizing the test with the BITE 2P. So whenever you're done taking all your measurements across the battery string, in order to finalize the test, you're going to have to follow a procedure to do that. So the first thing that you're going to have to do is you're going to have to short your potential probe and your receiver probe together and pull the trigger. What this does is it simulates the strap resistance reading for basically the last strap in the string. Because you usually don't have the same number of straps as you do cells, this is why this happens. However, if you don't follow this step, the last impedance value that you took for the last cell in the string is not going to be recorded. So it's important that you follow this step. Following that, pull the trigger with the tips shorted together, and then it's going to move on to asking you a couple of questions. First, press the down arrow, and it's going to ask you whether or not you want to complete the test. Tell it yes, and then it's going to ask you again to verify, are you sure? So go ahead and press the up arrow again to verify that you are sure that you're done testing, and then it will complete the test. So to view your results with the BITE 2P, like I said before, you can use the onboard printer to do that. Now, to do that, we have a cable that's provided, and what you're going to do is you're going to plug one end of that cord into the 7-pin connector on the bottom of the receiver, and then you're going to plug the other end into the RS-232 port or J3 on the BITE 2P. And then what you're going to do is follow the prompts on the receiver unit to export that data to the printer on the BITE 2P. So now we've talked about the BITE 2P. Let's take a look at our second option for battery impedance testing, the BITE 3. Like the BITE 2P, the BITE 3 can measure ripple current, cell impedance, your float voltages, and intercell strap resistance. However, the BITE 3 is a little more versatile in how it takes those measurements, and we'll highlight some of those features when we discuss the test setup. With the BITE 3, you can test battery banks with a capacity up to 2,000 amp hours, as opposed with the BITE 2P, a 7,000 amp hour capacity. The BITE 3 does have an increased internal memory of 32 megabytes, and it's also compatible with the PowerDB software. A couple of unique features of the BITE 3 are the LCD display that does allow easy access to our test setup and viewing test results. The BITE 3 also has the ability to measure float current on the battery string. And then another unique feature is the spectrum analyzer. Now, the spectrum analyzer is going to give you the ability to examine the content of the ripple current on the batteries, and this can help you verify the health of your battery charger. So with our BITE 3, this is the hardware that we have with it, and you can see that there's a little bit less hardware with it than with the BITE 2P. Now, this mostly has to do with how the BITE 3 injects current. Instead of using an independent unit to push current like the BITE 2P, the BITE 3 has been designed to use the test probes to inject that current. So with the BITE 3, we have the transceiver, and the transceiver allows us to configure the test and, like I said earlier, view our test results. Next, we have the test probe set, and the test probe set is going to be used like with the BITE 2P to take our measurements across the battery string. And then lastly, I want to talk about the CT. The CT used for the BITE 3 is different than the BITE 2P because the CT for the BITE 3 is not necessary for taking normal impedance measurements. The CT with the BITE 3 is only intended to use as an optional device whenever you're using the escape current or impedance modes of operation. The escape current mode is used for measuring a battery string where parallel paths may exist. But then the impedance mode is used for noisy battery systems to help us filter out any noise so that we can get accurate test measurements. So we talked about so let's talk about charging the battery of the BITE 3. Now the BITE 3 has a detachable battery that can be charged independently. This is helpful because it'll allow us to have a spare battery that's always charged and ready to go. Now to charge the BITE 3 battery, remove it from the bottom of the transceiver and connect the power supply into the battery charging port on top of the battery seen here. Then we're going to use the indicator on the side of the battery to show us what the state of the charge is of that battery. Now, if you want to slow charge the battery, all you have to do is press the green battery button here. So whenever we set up the BITE 3 to take our measurements, if you want to use that optional CT, you're going to go ahead and connect it to the BITE 3 and the port labeled CT here. And to connect our lead set, you're going to connect it to the J1 connector here. So when you do use the optional CT for measuring the BITE 3 with the BITE 3, you're going to apply it in the same manner as you apply the CT with the BITE 2P. And again, as we see here, it's going to be to the cells, the strap between cells 3 and 4. So let's now talk about how we're going to set up the BITE 3 to begin the test. So to do that, you're going to press the black power on button so that we can boot up the instrument. And after we've booted up the instrument, then we're going to go ahead and press the yellow menu button to bring up the menu for a new test. So go ahead and highlight the new test function and then click the blue enter button to proceed with the setup. So the first thing it's going to ask you to do is to select a site and string. If the site and string that you're looking for isn't available for your battery bank, what you have to do is go to the configure option at the main menu and select the strings options to add this information. So once you're in this prompt for the site and string, go ahead and use the yellow cross pad to select your site. And once you have selected the site, press the enter button and then select your string. Cycle through it in the same manner to select your string. Now, once you've done that, go ahead and press the yellow menu button, and it's going to ask you basically if you want to continue. So highlight, select, and continue, and press the enter button to proceed with the test. So the next thing that it's going to ask you to enter is the ambient temperature. So go ahead and measure that and enter the ambient temperature here. Then it's going to ask you, after you enter the temperature, press the enter button, and then it's going to want you to measure for ripple and float current. To do this, you're going to place your probes across one of the straps in the string in this manner with the red lead on the positive post and the black lead on the negative post. And once you have a stable reading, go ahead and pull the trigger on the red probe to record that value. Then you're going to want to apply the probes for the impedance measurements. Now, using this set of probes is pretty much the same way that we're going to use it with the BITE 2P. So you're going to utilize the pistol grip probes and apply them to the posts as we see here. And the red probe is going to be applied to the positive post of the battery cell, and then the black probe is going to be applied to the negative post of that same cell. And once we have a stable reading, go ahead and pull the trigger on the red probe to record that value. Now let's take a look at the inner cell strap resistance measurement. It's going to be, again, in the same manner as we use for the BITE 2P. You're going to leave that black probe on the negative post of the cell that you just measured, and then you're going to move the red probe to the positive post of the following cell. So in this case, we just measured cell number 2, and now we're going to measure the strap between cells 2 and 3. And we can see that the black probe is on the negative post of cell number 2, and that the red lead is on the positive post of cell number 3 for that measurement. So to finalize the test with a BITE 3, there isn't the need to short the test probes together like we do with the BITE 2P. To finalize the test with the BITE 3, all you need to do is press the yellow menu button and then highlight Save and Close, as we see here on the menu, and then just press the yellow Enter button to finalize the test. Now, for viewing your results on the BITE 3, you're going to utilize the LCD screen on the transceiver or download your results using PowerDB software. So to be able to view the results on the transceiver, go ahead and use the crosspad to select and highlight the Analyze option, and then press the Enter button. That's going to bring up this prompt that we see here, and it's going to ask you to select your site, string, and the date of the test that you want to analyze. So go ahead and find those options, and whenever you're configured with that, go ahead and press the Enter button. After you press the Enter button, it's going to ask you, bring up this prompt, and to select and continue those settings, press the Enter button. It's going to bring up a screen that's similar to this one here, and you can use the yellow crosspad to scroll through this screen to review your test results before you even leave the site. This is really helpful, again, like I said with the BITE 2P, that we can review our results before we move on. That way, if we need to reassess our measurements or do some more investigation on our battery string, we do have the opportunity to do that. Now, I did say that you can use PowerDB to download your results. If you want to do that, there is a supplied RS-232 cable, and what you're going to do is connect it to the port that's highlighted here, and then plug the other end into the COM port on your computer, and then you're going to use the PowerDB software to connect to the instrument and download those results. We'll take a look here in a minute at how to do that, and what that procedure is. Okay, so the next section that we're going to talk about is PowerDB for the test instrument and the battery test form. So whenever you open PowerDB, go ahead and select either the BITE 2 or the BITE 3, and then it's going to bring up a window similar to this one. This one particularly is for the BITE 3. So go ahead and select the serial port that you're using, and then hit the OK button. And then the next screen is going to ask you about a hydrometer. If you are using a hydrometer and you're going to have that connected to your computer, go ahead and select the COM port for that, and then hit the OK button. If you don't have a hydrometer that you're using, it's okay to just go ahead and hit OK, and it'll proceed with the download of our results. The next prompt is going to ask us if we want to import data from the BITE. Go ahead and hit the green check mark to proceed with this process. So this screen is going to ask us to make sure that we're connected to the correct COM port on the BITE 3, that the BITE 3 is powered up, and that we can see a display on the main screen. After you've done all of that, go ahead and hit the next button to begin the data transfer. So this screen here is where we pick which data we want to download out of the instrument. So go ahead and check the boxes that you want to check for your site and string and test date, and then hit the next button to move on with the process. The next screen is going to ask you to verify the directory that you want to save it to. So just verify that this is the correct directory, and then hit next to move on with the process. So this is where you're going to make sure that you have the information that you want to download, that you have it labeled correctly. Here's where you can enter your owner, region, site, and string information. If you want to change that, there's drop downs to be able to do that, or to select options to add the information so that you're properly have your information documented. After you've done that and you verify that that's correct, go ahead and click the Finish button. So next, it's going to tell you that the import is complete, and go ahead and press the green check mark, click on that. And then it's going to ask you how you want to save that file. Go ahead and ensure that the name of the file is named the way that you want to name it, and hit the, excuse me, your file is going to be here. Find the way that you saved your file, being the the owner, region, site, string. That's the examples that we have here. It'll be named that way, and then find and click on that and hit the open button. Next, you're going to highlight the test date that you selected for your test data, and hit the open button to move on to opening that data on the test form. So now let's take a look at the test form that's in PowerDB. This is the header for that form. And in this form, we can document the different information that we have, such as temperature and humidity, our job number, our asset ID for that piece of equipment. But also, we have the option to look at the status, the test status, where we can, if we do have a piece of equipment that hasn't passed, or it's failed or needs attention, we can document it here, and it's easy to access whenever we go back and look at our job report. The next section of this form is going to allow us to document the string information, how many cells are in it, how many straps are in it, how many pilot cell measurements that we took, as well as the charger information, such as the manufacturer and model, and then it'll allow us to record our ripple and float current measurements also. So this is what some of our test results will look like. Something that's important to talk about in this part of the form is the ability to customize the charts that we look at on this form. So the button that we have here, the Select Charts button, is going to allow us to open up a prompt to customize the way that we want to look at our data, or to even repress data that we don't need to customize the form. Next, we have the limits block. This is where we can set the limits for our tests, and that way, whenever we're looking at those charts, it's going to tell us in the color code whether or not those values are something that we need to, that are of concern. This here is where we're going to identify whether we want to use baseline data or not, or if you want to use the test that you've just done as a baseline for the set of batteries that you're testing. Now, this table is where our impedance values are going to be, and the first block is a table summary of the string overall, and then the next part of the table has our impedance values and cell voltages. So this is one of the tables that we would see on our test form. This table here is for our cell voltages, and this is a representation of what we want to see whenever we're looking at our cell voltages, because the test results are uniform pretty much across the entire string, and they all fall within the kind of range that we want to see whenever we test for those cell voltages. This is another way that one of the graphs may be represented on that test form. Now, something that's important to point out here is we see that there is an impedance value that's way outside of what all the other impedance values are. Now, Most likely this isn't because of the value of the battery. This is more likely a product of an inadequate testing technique. This is why it's really important that we make sure that we practice good quality testing techniques whenever we're taking these measurements. This is what the graph would look like for your strap resistances. Again, as we talked about before, the measurements that we got across the intercell straps is pretty uniform across the entire string. And this is what we want to see whenever we're taking those measurements, because it is a comparison test. For the purposes of this presentation, the references that we used were the IEEE 450, 1188, and 1106, and NERC standard PRC 005-6, and the Megger battery testing guide. To conclude our presentation, would like to point out that ohmic testing is a good alternative for determining battery health, and it can be performed online at a low cost. However, there is no definitive value to evaluate the test results that we get whenever we do those tests, and that sometimes we have to use historical or baseline values to evaluate those results. That's why it's important that we properly prepare the battery string before we do any testing. That way we can produce quality test results. Also, by following quality test procedures, we're going to be able to produce reliable results for evaluating the health of our batteries. Okay, thank you for your time, and I'd like to turn the presentation over to Michael for our Q&A session.
All right, thanks a lot, Jason. So as previously mentioned, the presentation portion of our webinar has officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's also a field where you can request a quote or a demo of any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar on Wednesday, Case Study and Field Experiences, Transformer Winding Resistance Measurement. The presenter for that will be Samir Kulkarni. All right, let's jump into our questions. And the first one I have, I'm going to be directing to Sanket. Sanket, what is the difference between conductance test and impedance tests?
So the technology is called ohmic testing, and different manufacturers follow different methods of ohmic testing. And but essentially we are all trying to do the same thing. We're trying to check the electrical path that is the battery string, and that is done by injecting a current through the battery and measuring the voltage across a cell, and then measuring the ohmic value. Now we measure the impedance in conductance testers, or while doing conductance testing, the conductance is measured, which is really the reciprocal of the impedance. The real part of the admittance is what conductance is. So we are representing the data in terms of different parameters, but we are essentially doing the same thing, and that is injecting an AC current through the battery and determining the parameters.
All right, thank you. Volney, what is the correct method of measuring battery temperature?
Good. So since it is a very important parameter or piece of information to analyze the results, you want all the results to be at the same temperature or very close to the same temperature always. It is important to measure the temperature correctly. So if you're talking about vented batteries that you have access to the electrolyte, the best method or the best way to measure the temperature, to get the temperature of the cell or of the different cells, if you are averaging the value, which is the recommendation, you want to measure the temperature directly on the electrolyte. So any hydrometer that digital hydrometer that does that will give you that information. That will be the best thing to do. If you have a valve regulated lead acid battery, for example, that you have no access to the electrolyte, the best way to get the temperature is going directly to the negative post of the cell or the cells that you want to measure the temperature that you want. The negative post is where all the chemical reaction happens, and if there's any activity, any internal activity in the battery, the temperature will be increased mainly on that terminal post. So that is the best way to go for the temperature.
All right, thanks, Folney. Additionally, are those testing procedures applicable for any type of battery, or are these test methods only applicable to lead acid batteries?
So these, as it was shown in the presentation, the method is injecting a current or having a current circulating through the cell and measuring a voltage drop, and that allows you to measure an impedance. So in that sense, you could say that you can apply this to all type of batteries. However, the important thing here on the answer is how to analyze the results. So it's not as Jason indicated at the beginning, it's not an absolute value that you're looking for. It's a relative result that you get, and you have to trend this value preferably to be able to make any decision. You compare to a baseline, you compare to previous readings, and in that sense, where there's the most use of the test, and where there's a lot of results, and where it has been applied the most is for lead acid batteries. So for other batteries, it might be applicable, but you will need to find out the way to analyze the results, how to make sense out of the values that you are getting. One typical example is NiCad batteries. So NiCad batteries, you can do the measurement, you get a result. In under certain conditions, the impedance on a NiCad battery might change, and is a clear indication that the battery is under a failure mode, and the capacity probably is already gone, or you have very reduced capacity. However, it's not that it will always change when the battery deteriorates. So it's not, you could have false positives or false negatives, that the battery will be already gone or dead, and the impedance doesn't change, because that's the way the chemistry happens. So it's matter of understanding the battery, matter of understanding the results, and developing your own analysis method on that. For lead acid batteries, it's more developed, and we have some reference values to analyze the results. So that's why it's more applicable to lead acid batteries.
All right, thank you. Sanket, how long does it take to get a stable impedance reading on the BITE 2P and BITE 3?
So the time differs for each measurement, and one of the reasons is because of the way the test is done. When you test with the BITE 2, you are injecting the current continuously throughout the string, and you take measurements across each cell. You take voltage measurements across each cell. So the measurement time itself is a little shorter when you test with the BITE 2. When you test with the BITE 3, however, you do the test on each cell at a time, which means that when you start the measurement, it injects the current at that point in time, and then you go about measuring, recording the measurement. So each measurement takes a little longer on the BITE 3, but it's in terms of seconds. And let's say if the BITE 2 would take maybe 3 seconds for a measurement, and the BITE 3 would take slightly longer, maybe 7 to 8 seconds per measurement.
All right, thank you. Additionally, Sanket, would I be able to run an impedance test with the BITE 2 on a 480 volt battery bank?
So again, this comes down to the way the instruments function. The BITE 2, you connect the current leads across the whole battery string, and then you take measurements across each cell. It's not the case with BITE 3. On BITE 3, you can test the same way irrespective of what the voltage rating is for that battery bank. But on the BITE 2, there is a voltage limit of 250 volts. So you cannot connect the current leads on a string which is greater than 250 volts. But that doesn't mean that you cannot test the battery string. What you will need to do is you will need to sectionalize, which means that you will divide the string into two parts. And in the case of a 480 volt, the voltage across each part would be 240 volts, which is within the instrument limits. And then you can carry out measurements on each of those sections separately. And I mean, the results won't get affected, but you will just need to do this sectionalizing bit to be able to get all the measurements.
All right, thanks, Sanket. Volney, the last battery string I measured had completely enclosed battery posts. What should be done if this is found?
Yeah, that's a common situation. Some batteries, they will have a insulated cover or covers to insulate the strap and the post, so you don't have access to that. Some of them will have a little hole in the insulation where you can put like the typical probe of a digital multimeter. So in those cases where you can have a little bit of access to the post, what you can do, I will recommend using BITE 2 because you are injecting current through the string, and the probes. The only thing that they do is to measure the voltage drop, and we have some accessories and some probes that you can measure through those little holes that you have in the insulation. BITE 3, on the contrary, on the probe you have a set of probes or leads that will inject current, and there's the other set of leads that will measure the voltage. So with that one is more difficult. So for the cases where you have a little bit of access, I would recommend BITE 2. There are some other batteries that if you definitely want to do impedance or ohmic measurements, you will definitely need to work with the manufacturer to have these insulators have some kind of access for you to be able to measure.
All right, thank you. Sanket, can the BITE 3 tester measure multi-tap straps per cell impedance like the BITE 2P?
Yes, and again, in this aspect as well, the instruments function differently. Now with the BITE 2P, you have a CT which you wrap around multiple straps, and then you let the BITE 2 know how many straps you have wrapped it around, or you introduce a certain multiplier so that the software calculates the resistance accurately. But with the BITE 3, you do not have a CT. What you have is you have two probes with which you take the measurements, but you have on the software you have the ability of taking multiple strap measurements for a connection between two cells, which is not there on BITE 2. So on BITE 2, you have the option to only record one strap measurement after every impedance measurement. Whereas on the BITE 3, you can record multiple strap resistance measurements, and that comes in handy when we are trying to test strings with multiple straps on the intercell connections. So what you will do is you will do diagonal measurements, and the IEEE guide kind of has a section which deals with exactly this situation, how to do multiple strap measurements. So it has diagrams, and you can look at that guide and see the diagrams, and that shows you clearly how the connections need to be done, or how the measurements need to be done on multiple straps. It's done diagonally to make sure that you get kind of even values, consistent values for different combinations, and also you cover all the individual posts. So that's the way you would work with a byte through.
All right, thanks, Henket. And while I have you, can I trend impedance test results using PowerDB Lite?
So trending and analysis is a very important part of impedance testing. And we do have two versions, three versions really of PowerDB. PowerDB Pro, the full-blown database management version, is the one which allows you to maintain a database of test results, and you can carry out trending and all that. But because trending is so important for impedance testing, we do provide trending features even on PowerDB Lite, which is the free version. So some people are not aware of it, and they just create separate files for each measurement. But that's not how data should be handled when you're working with a byte 3 or a byte 2. What you need to do is you need to have one file created for each asset, and this is when you're working with PowerDB Lite. You create one file the first time you run an impedance test on a bank, you create that file, and then henceforth, whenever you run an impedance test, you have the ability to download those results onto that same file. So now you have multiple tests stored on a single file for that asset. So it is possible to have all the data in one file, and then you can obviously do trending and analysis using all the tools that are provided on PowerDB on the battery impedance test form.
All right, thank you. Volny, what are the ideal conditions in which batteries should be kept?
Well, that's a little bit out of our testing scope, but definitely we understand batteries, and well, my first answer to this question is that you can refer to the IEEE standards that Jason mentioned. The IEEE for the vented lead acid batteries is the 450, for the valve regulated is 1188, and there's definitely good information there on how you should maintain the batteries. There's also standards for the proper installation of these batteries, 484, 485. We'll talk about lead acid and vented and valve regulated. The worst enemy of a battery is temperature. So temperature is the worst aspect that you can have, increased temperature that you can have in a battery environment. So you would, if you know that the battery is going to be in an environment that it's elevated temperature, you need to discuss that with the manufacturer to so he can recommend the best battery or the best product for that condition. Usually, if that is the condition, NiCad batteries are more recommended. Of course, they're more expensive. Then so you want to maintain good temperature conditions if you have a lead acid battery, and especially if they are valve regulated, because valve regulated temperature will cause that they will increase the gassing, and in valve regulated you don't get the option to replenish the electrolyte, so they will end up starving from electrolyte, and they end up drying out and thermal runaway. So that's the first aspect. And another very critical operational aspect to consider is the float voltages that you set on the charger. Overcharging or basically going above the recommended floating voltage of the battery will generate the oxidation, or accelerates the damage of the positive plate, and undercharging or going below the floating level, it will create sulfation. So you want to set the voltage properly, and that's why part of the verification that you do every time you go to check the battery or do the inspections, you check the float voltages, and as part of the results, the form shows you the total voltage, and you can compare that to what it should be, and then If it's not like that, then you should take action. So there are many other things to consider, but temperature and float voltages are the ones that I would recommend initially to take care of.
All right, thank you. Jason, what are permissible limit values of strap resistance?
There are some permissible limits for strap resistances. As we mentioned in the presentation, that your strap resistance values, it is a comparison value, and it is something that we have to keep an eye on to make sure that we have good integrity of the battery string. Now, that permissible limit has to do with comparing the values, and what that is the highest value that you want to see across the resistances, across the battery string for your strap resistance is 50% of the lowest reading that you have in the battery string. So that's why when we talk about comparing the tests, that we make sure that you apply good testing techniques, because if not applying good consistent testing techniques could cause you to throw off your resistance values, and then you may, when you're comparing these values, think that you have a bad strap when you actually don't.
All right. Volney, are there any other tests recommended for batteries? What are the equipments required in that case? And what are the IEC or IEEE standards?
Okay, so electrical test or tests that you can run on the battery to determine the condition of the battery, as Jason mentioned at the beginning of the presentation, there are two: the capacity test or performance test, and the alternative test is the impedance test or the ohmic value measurement. Other tests that you can perform are like voltage, float voltage measurement, float current, ripple current, and visual inspection, which is not an actual electrical test, but it's very critical to perform. So those are all of these tests are mentioned in these standards that are recommended in one of the last slides. And the main test that you can perform on a battery is the capacity test. However, it's a resource demanding test, and it's performed in a very wide span of time that you might lose deterioration that you can correct while you perform the test. So that's why the impedance or ohmic test is recommended as a complementary test or as an alternative test. On regards to the IEC standards, there are definitely standards on the IEC side. I would say that they are the IEEE are more comprehensive on all of the maintenance methods that are described. Well, I don't have the exact reference on IEC standards, but I know that they have one standard for maintenance on vented lead acid. They also have a standard for NiCad batteries and valve regulated. But the IEEE standards are more comprehensive on the maintenance methods that they recommend.
All right, thank you. Jason, can we use PowerDB with Megger's BITE 2P?
Yes, we can use PowerDB with the Megger BITE 2P. There were a couple of things that we went over that you would, a couple of the processes that we talked about that you would apply to be able to use the BITE 2P with PowerDB. Now, the first thing that we talked about was whenever we exported the data from the receiver with the BITE 2P to the printer with that instrument. Now, the setup to use it with PowerDB is similar. Now, you're going to find the export menu on the receiver and select that. And then once you select that, it's going to give you an option to either export that data to the printer or export the data to your computer. Now, to connect the receiver to your computer, there's a cable that's provided, and on one end is going to be the connection for the receiver, and the other end is going to be an RS-232 connector that you can connect to the COM port on your computer. Now, once you've done that, you're going to follow the similar procedures that we talked about for the BITE 3. You're going to make sure that the receiver's powered up and that you have everything connected, and then you're going to start that process where you select the COM port that you have it plugged into, and then follow the prompts as we talked about. And once you have all of that configured and set up, you'll be able to finalize that process or finish that process, and the information that you have stored in the receiver will be able to export to PowerDB. And the information that you get is going to look very similar to what we looked at whenever we went over the PowerDB form. You're going to have the tables for your impedance values and your cell voltages. You're going to have another table for your strap resistances. There's going to be some other information that we didn't really talk about as in our presentation, like there is a table for temperature and a table for specific gravity in there. We just didn't have time in the scope of our presentation to go over that. So to answer your question, yes, you can use the Megger BITE 2P with PowerDB.
All right, thanks, Jason. Additionally, can I get the strap values shown in the form? I believe they might be referring to the presentation here.
I don't have that part of the form in the presentation. I would like to point out, however, that in that PowerDB form, there is a section that displays that information. So similar to the part of the form that we showed that had the impedance values, you're going to have an additional table that has the strap resistance values for that. Also, in our presentation, we looked at examples of some of the charts that form will produce. Specifically, we did look at one of the charts for strap resistance values. Now, you can configure that form under the chart options to display a chart similar to the other ones that we showed as well. That was just one particular example that I wanted to use to be able to show what your strap resistances should look like, and an example of what you may see on the form.
All right, thanks, Jason. Sanket, for strap resistance and battery impedance, is it required to have the 72 hours float / no water added?
Yes. So the reason why that is necessary is because we want the cells to be at a certain in the fully charged state. We do not want to be at different levels of charging, because that's going to cause a change in the characteristics of each cell, and that's going to result in different impedance values being measured. So to measure the impedance values consistently, to measure them accurately, we need to make sure that the cells are fully charged, and we do so by maintaining them in a float charge condition for a period of at least 72 hours for lead acid batteries. As far as adding water goes, for flooded lead acid batteries, we want to make sure that the electrolyte level is all the way up before we even start the float charging procedure, and that's a good practice. So make sure that the electrolyte level is always all the way up to the mark, and make sure that the cells have been on float charge for a period of 72 hours.
All right, thanks, Sanket. It does look like that's all the time we have for questions today. We apologize if we didn't get your questions live, but we will follow up with you offline. But thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you have a great week.